Okay, so let's see here. Okay, so I think that this is probably a question that is present on a lot of our minds right now, given last weekend's heat wave, and that this is one of the warmest summers on record. How will Pacific Northwest heat waves change under anthropogenic global warming? And for our region, at least more so than other parts of the world, it's kind of a complicated question. We have very complex terrain, vastly different microclimates, and very drastic land sea contrast. The biggest ocean in the world is our next door neighbor. And so as I analyze this question, I'm primarily looking at two things. How will the mean state change? And then also, how will the weather conditions that bring about heat waves change? And so I guess the first question to address is, what is the mean state in the summertime? And what are the conditions that bring about heat waves? Well, for the summertime in Western Washington, the mean state is awesome. If you haven't been here, I mean, to get temperatures like this anywhere east of the Cascades, we either have to live in northern Maine or 10,000 feet in the Rockies. So these mid-70s are produced by the following. So what I have here is data from Sept reanalysis for 1970 to 1999, and this is July and August only. And up here we're looking at average daily maximum 2-meter temperature, and then down here, average sea level pressure in millibars and wind vectors. And so what we see here is for in the summertime, we typically have the Pacific high spinning anticyclonically offshore, driving our northerly flow along the coast. And then inland, we typically have lower pressure. And this is a heat low that is produced by the intense surface heating in the Great Basin region. And so just remember that we have onshore flow typically in the summertime with higher pressure offshore, lower pressure inland, okay? But we get our big heat waves when high pressure builds in the interior associated with the ridge aloft, and that higher pressure inland drives offshore flow, and that gives us our big heat waves because of downslope flow and adiabatic warming on the western slopes of the Cascades and coastal mountains. Subsidence from downslope flow suppresses cloud development, so there's clear skies, and then offshore flow keeps the marine air offshore. And this has been discussed in a few papers in the literature. And so this is just like what we experienced last weekend. So here's last Friday, and of course on Saturday all sorts of records were broken around here. I think Seattle was about 17 degrees above normal. We hit 90. Let's see here. So this is Friday morning, and we're looking at temperature at 925 millibars, sea level pressure, and wind at 10 meters. And so what we see here is that the lowest pressure, the warmest temperatures, are along the coast. And like I mentioned, we get high pressure building in the interior, and that drives the offshore flow, which gives us the warmer temperatures and the formation of this inverted pressure trough here that's known as the West Coast Thermal Trough. So these are the conditions that bring about our big heat waves here in the Northwest, and I think we might get something like this weekend as well. So in analyzing these questions, how will the mean state change and how will the conditions that bring about heat waves change? These are the data sets I'm going to use. I'll be using the CMIP 5 GCMs, the historical and RCP 8.5 runs, primarily Ensemble 1 when it's available. One thing that's important is the GCMs do not account for regional terrain influences on our weather, like rain shadows, convergence zones, orographic precipits, snow albedo feedbacks, etc. And that's because in the GCMs, there's no Cascade Mountains. There's no Oregon Plateau, Columbia Basin, Puget Sound region, Willamette Valley. Just from the coast to the crest of the Rockies, it's just kind of a gradual slope. And so any of these effects in our region are not going to be there. And so to combat that, I'll also be using regional climate models. And that's what Cliff was describing, where you run a high-resolution model with initial and boundary conditions prescribed by a GCM. And so specifically what we did, we ran the WRF, the Weather Research and Forecasting Model, at 36 and 12 kilometer resolution in a domain centered over the Pacific Northwest with initial and boundary conditions first prescribed from the Sept reanalysis. And so this gives us a high-resolution historical data set that we can use now. And then we also did this for 2 GCMs from the CMIP 3 project, the ECM5 and CCSM3. And these are 100-year simulations using the A1B scenario from the IPCC AR4 report. And all of these data sets here, the model output is 6 hourly, 0, 6, 12, and 18Z. Now, let's look at changes in the mean state. I think there's a lot of interesting changes in the mean state in the summertime that may happen in the future, but we're just going to talk about temperature right now. So this is temperature minus present for the daily maximum 2-meter temperature from the CMIP 5 GCMs, the ensemble mean, and only for July and August. And so we see a pretty uniform, well, not uniform, but we see warming over the whole region, over the whole domain, of about 3 to 6 degrees C. And this is just one scenario. Dennis referred to this scenario as business as usual, so I guess we can call it that. But the numbers aren't as important as just the pattern. We see greater warming in the interior, and so these enhanced temperature and pressure gradients that will happen in the future will likely work against our offshore flow events. And so I think that's important to keep in mind. Now, given this change in the mean state, if nothing else changed in the future, just this increase in the mean state, how would that affect heat waves? Well, of course, they're going to be more intense, more frequent, and of longer duration. For example, this is a heat wave from last month at SeaTac, and I just arbitrarily defined a threshold at 85 degrees, and so I just said anything above 85 is a heat wave. And so this would be a 2-day heat wave. If we knew that the temperatures, if we knew the mean was going to warm by 5 degrees Fahrenheit, if we just added that to this heat wave, we'd get a much longer and a much more intense heat wave. So, is it that simple? Can we project future heat wave frequency, intensity, and duration by increasing the contemporary temperature distribution by the expected change in the mean temperature? And I ask this question because it has been done in the literature before to project future heat waves over our region to get a rough idea, but this assumes that there's no change to the shape of the temperature distribution under anthropogenic global warming. Is that a safe assumption? Well, let's look at our temperature distributions. So this is Portland 2-meter temperature distributions from the downscaled 12-kilometer CCSM3 run, and this is for the contemporary period, so 1970 to 1999, and the mean of this contemporary distribution is 76.12 degrees. In the future, the temperature distribution, the mean of the future distribution from 2040 to 2069 is expected to be 80.37 for a difference of 4.25 degrees. And so, if I was just to add this expected change in the mean on top of this contemporary temperature distribution, this is what you get. So we just get a shift in the temperature distribution by adding this number onto the contemporary distribution. And so, whereas before, the number of days above 95 degrees for Portland was 34, but we're expected to get 102, a tripling, okay? That doesn't sound fun. But when you look at what the CCSM3 actually shows for this future period, it's actually this. You see that? The distribution narrows. So the standard deviation was 7.76, but the CCSM3 is projecting the distribution to have a standard deviation of 6.98. Where we were expecting 102 days above 95, it's actually only a doubling of 68 days above 95 because of that narrowing of the temperature distribution. So this question really depends on which model you look at. So I plotted 2-meter temperature standard deviations, the future minus the present, for the CCSM3 and for the ECM5 run. And so we see for the CCSM3, the standard deviations lessen over pretty much everywhere inland by about 0.5 degree to a degree, whereas the ECM5, there's almost no change to the distribution in the future, maybe a little bit, along the coast and on the western slopes of the Cascade Mountains, but generally the temperature distributions stay the same in the ECM5. Now, I want to talk a bit about changes in offshore flow events. How will the conditions that bring about heat waves change under anthropogenic global warming? So here's the plan for the rest of the talk. I'm going to define an offshore flow event and then create a climatology of past and future offshore flow events using the downscaled NSEP and GCM WRF runs, and then look for changes in the intensity, frequency, and duration of offshore flow events under anthropogenic global warming. So how did I define offshore flow for our region? So what I did was every 6 hours, the U-wind average, or the wind in the X direction, the U-wind average is found of all grid points along the Cascade Crest in Oregon and Washington at 850 millibars. Now for clarity, we're going to call this average of the U-wind along the crest the U-wind index, or the UW index. Go Huskies. Okay, so the 12-hour average UW index is found for 0, 6, and 12Z, and also for 12, 18, and 0Z. So that gives us a single offshore-onshore value for the nighttime and for the daytime, okay? And then a string of one or more 12-hour periods with negative UW index is considered an offshore flow event. So then we have, what is the correlation between daytime offshore flow and 2-meter daily maximum temperature? So if the offshore flow has been going all day long, what's the correlation between that and the daily maximum temperature? So what we see here for July, there's a very strong correlation, a very strong negative correlation between onshore flow, positive U-wind, and temperature. So if we get onshore flow, the temperatures are going to be less than normal. They're going to be cold. But for offshore flow, they're going to be warmer than normal. And December, it's the exact opposite, but I don't have time to go into why that is. So to hammer that point home, what I'm showing here is this is using the NCEP reanalysis WRF runs. These are composites of temperature departures from normal at 0Z for daytime offshore and onshore flow. So simply said, for offshore flow in July, temperatures are quite a bit above normal. For onshore flow in July, temperatures are a bit below normal, about 2 degrees C. I think an interesting point is that for the 10% warmest days at Portland for July and August 1980 to 2009, 171 of the 186 days were associated with an offshore flow event. The other 15 days had offshore flow at 12Z in the morning, but had stronger offshore flow at 0Z. A strong marine push is what happened. And so the UW index was positive. I also want to show you composites of temperature departures from normal at 0Z for daytime strong and weak offshore flow. So if we have, so I define strong offshore flow as a UW index of less than -4 meters per second and weak offshore flow as between 0 and -4 meters per second. And so for strong offshore flow, we get temperatures that are quite a bit above normal. For weak offshore flow, we get temperatures that are still above normal, but not nearly as much as when you get strong offshore flow. So I think I've beaten that relationship into the ground. Okay, so future offshore flow, what's going to happen? So what we have here, let's just focus on the left side of the figure here. So this is ECM5, days and nights with negative UW index for July and August. And so that we see here for the 1970 to 1999, for nighttime offshore flow, there were 471 days with negative UW index, but in the future, for 2040 to 2069, there's only 415 for a drop of 12%. For the day, there's a drop of 11% from the contemporary to the future period. And for CCSM3, these drops are more drastic, of 18% and 17% for night and day, respectively. Then over here, what I did was ECM5 days and nights with a UW index of less than -4 meters per second. So that would be just strong offshore flow. And we see that the declines are more substantial, of 18% and 18% for night and day for ECM5. And then for CCSM3, it's 29% and 31% declines from the contemporary to the future period. If we just talk about offshore flow events, we also see these declines as well. So for CCSM3, the total number of events from the contemporary to the future period, we expect a decline of about 15%. For ECM5, it's about 10%. And that we see for the length of the event, length of event is here on the x-axis and frequency on the y-axis, and that we see for all lengths of events, there's generally a decline in the frequency and duration of offshore flow events in the CCSM3, and less so, but still the decline for ECM5. So, despite all this, there's still very big questions that remain. Are these results robust? I've only shown you 2 downscaled runs from CMIP3 GCMs. We definitely need more downscaled runs, especially from the CMIP5 runs. Since these runs are so hard to make, they're very computationally expensive. They take about 3 to 4 months to make of just continuously running on a cluster. I want to see if the GCMs themselves can simulate these events, because then that would lessen the need for me using these downscaled runs. Maybe I can, take a point in Portland or Seattle and take like the 30 warmest days and composite them in the GCMs just to see how well the GCMs can simulate offshore flow event conditions. I think an important question is whether or not these results are robust. Why would there be fewer offshore flow events in the future in the CCSM3 and ECM5 runs? Could it just be a mesoscale effect? Could it just be stronger onshore flow due to the enhanced thermal and pressure gradients? Or could it also be a synoptic issue, that the position intensity of the storm track, the duration and strength of the ridges? I think there could be something to that, actually. I think it might be a little bit of both, but I'm working on that right now. I think I have time to do a quick summary of summer. So the GCMs do suggest an enhanced temperature gradient along the coast, which could work against Pacific Northwest heat waves. An offshore flow event was defined. An offshore flow was found to have a strong relationship to temperature in western Washington. One of the 2 downscaled runs suggests a substantial change to the distribution over a region, a narrowing of the temperature distribution in the future. And both downscaled runs suggest a decline in the frequency and duration of offshore flow events. that'll take your questions.
Thanks. Any questions for Matt? Let's start with Nick Bond here.
Thanks. With your offshore flow events, did you distinguish between northeasterly flow and southeasterly flow? Because it's the northeasterlies that really get us hot, and it's a different kind of weather with the southeasterlies. And just whether you looked at that aspect of these kinds of events.
Well, I guess I'm curious, like, is that just your intuition, or do you have a paper? Like, what do you got? What do you got for me?
Well, you also have a paper that showed for the northwest heat waves, and some of your work that shows it's basically, especially below 700 millibars, that it's northeasterly flow that really gets it hot down into the thermal low. And you can have also southeasterly flow that tends to give us some much more bring moisture from the
Yeah,
basin
yeah.
and so forth. And it's a different kind of weather. And just, but I'd be really curious about if there's more of these northeasterly flow.
That is interesting, and I would wonder. Well, I guess I won't get into that, but I haven't looked at that. I think I have a way of being able to do that. Actually, I'll check that out.
You guys should
Interesting.
follow up on that.
Sure.
Any other questions? Let's hit Guillaume.
Yeah, it is me, yeah. Just a quick question. So you looked at nighttime heat wave events. I wouldn't expect those to be associated with offshore flow. Am I wrong about that?
Well, so back when I showed those composites of these, this is for just daytime offshore flow. I did it also for nighttime offshore flow, and you do see, I mean, definitely like warmer than normal temperatures. There is absolutely a strong correlation between nighttime offshore flow and temperatures in the morning. It was just about as strong as the daytime offshore flow. I mean, let me back up, because, you know, I know that we often get very warm temperatures at night that are not really associated with offshore flow events. You know, they're more like high moisture events, but still, by doing this for nighttime, I did see warmer than normal temperatures for nighttime offshore flow. So there is something there, definitely.
Let's take the question in back here.
Very interesting work, because this has some very interesting implications for electricity demand.
Okay.
Have you thought about expanding this, especially the standard deviation changes in CCSM? That was interesting.
Uh-huh.
Have you thought about looking at cold snaps? Because that, or at least for me, being a power guy, that's actually even more critical for us right now.
I got to get my dissertation done, man.
I'm on this committee too, so
I'll be honest. It sounds interesting. I mean, you know, and I would say it would be really easy for me to look at that, and, you know, I can. It would just be a quick plot.
Thanks a lot, Matt. I think we